And over here you have some loop that's weird. No, maybe not like that. Let's see, what would be a better example of this?
A square.
Let's say like a big ring. Just a big ring, right? You see what the problem is. And I ask you, what is the magnetic flux? What if I have a current over here of I, and I ask you, what is the magnetic flux of the magnetic field produced by this current through this big ring? Well, you go like this, right? So along the axis, the magnetic field is going to be like that. And we did that problem. You have a ring and so on, right? But what happens is that, you also have this, right? And then you have something like that, and then you have something like that, in weird directions. And the magnetic flux through this, you gotta take B dotted with the area. So it's like a complicated problem. Yeah? Because the magnetic field is not always in the same direction. I mean, the magnetic flux through here is really the magnetic field through over here, right? Dotted with the area vector. Then I have to integrate over all this area. But the magnetic field this is to the right, this is at a different angle, this is at a different angle, this is at a different angle. So it becomes a complicated problem. So the question is, originally, what is the magnetic flux through this ring, right? That's a big ring, produced by the current in this little loop. And then what you can do is answer the question by flipping the question around. You can say, well, if I run the same current in the other loop, I can figure out the magnetic flux to this one. The magnetic flux is going to be the same. And if this is small, then I can just do the problem where I calculate the magnetic field to the current in this big loop. Over here, over this region, it will be roughly uniform, and I can just say B, the magnetic field that I calculate over there, times the area of that little thing. So the magnetic flux through this is going to be the same as the magnetic flux through that if the currents are the same. So I flip the question around. Let me give you another example from Physics 185, right? Baseball game. Yankees are playing, or the Angels, or the Dodgers, whichever. And the ball is pitched, and it's going towards home plate, right? And you're told the initial velocity of the ball is 90 miles an hour horizontally, and then wham, it gets hit by the bat, and it goes off at some angle at some speed. And then they ask you the question, what was the force that the baseball exerted on the bat? The baseball on the bat. My goodness, gee. How hard did the baseball hit the bat? You don't know any information about the bat. How fast it was going right before it hit the baseball, how fast it was going after that. You don't know any information about the bat, but you were told how fast the ball was traveling, what the mass of it was. Initially, later on, maybe you're told that the time of the collision is so much, right? So what you do is you flip the problem around. You say, oh, I can figure out what the force was exerted on the baseball by the bat. Right? The impulse exerted by the bat on the baseball is going to be the change in the linear momentum of the baseball. I know the mass of the baseball, the initial velocity, the final velocity. Right? I can figure that out. And by Newton's third law, action-reaction forces, well, the force that the baseball exerted on the bat, which is what I was asked to find, has to be the same in magnitude and opposite in direction as the force that the baseball exerted on the baseball. So it's easier to flip the question around, figure out the force on the baseball, and then the force that the baseball exerted on the bat is just equal in magnitude, opposite in direction. No, you look unhappy.
I'm happy with the bat. I'm not happy with that picture.
So it's the same idea over here, right? So the question is, what is the magnetic flux through this big loop that's complicated? The magnetic field goes in different directions. And this one was given as a tiny little circle, for example. A tiny little loop. So the magnetic field through this loop is going to be in different directions. It's going to be difficult, very difficult to figure out what the magnetic flux through it is going to be. So what you do is you flip the question around and you say, okay, if I run the same current over here, the flux through this loop is going to be the same as the flux through that loop when I have the same current in this one. That's what this is saying. Right? The fluxes will be the same if the currents are the same in both of them. So I run the same current in the other one, but maybe if this is like a problem where you have a nice ring, and we did the problem where you calculated the magnetic field on the axis of the ring due to a current around it, and we know what the expression is, but since the ring is very small over there, it just, the magnetic flux is going to be that magnetic field times that area, that little area.
But the current has to be in the